Hi everyone, it's 4 o'clock here, so we're going to get started. And also we realized that WebEx has a new interface for us this past week, so some people may be having fun dealing with logging in on that new interface. So I'm going to start the introduction slowly here. Hello and welcome to Advances in Emergent Needs in Paleogeoscience Cyber Infrastructure, a webinar series organized by C4P. C4P, Collaboration in Cyber Infrastructure for Paleogeosciences, is an EarthCube research coordination network supported by the National Science Foundation. I'm Leslie Shee, and I'll be the moderator today. In today's talk, we have two presentations, each 20 minutes, with roughly 10 minutes for questions. We'll want to keep this to an hour, so I'll be fairly strict about enforcing time limits, and we'll give each speaker a 3-minute warning. If you have questions, please send them through the WebEx chat window to the Research Coordination Network. We'll read them aloud after the presentation. You can send in a question at any time. All presentations and follow-up discussion will be publicly archived on the EarthCube website and at the C4P YouTube channel at youtube.com/Cyber4Paleo. Our first speaker today is Chris Jenkins from University of Colorado, and he'll be speaking about Geologic Time and Paleocoordinate methods in the Global Seafloor Geology Database, dbSEABED. Our second speaker is Jim Bowring from the College of Charleston, who will be telling us about automating geochronology workflow from raw data to repository, the power of collaborative software engineering. So we're going to begin with Chris Jenkins. We will pass him the screen share now. Okay, so Chris, you can begin when ready.
Okay.
And we'll let you know when we can see your screen.
Very good. All right. I'm not sure I have the video transmitting, but anyway.
The video is showing, the video is showing, but not the title slide yet.
Ah. I think that's got it. So, good afternoon, everybody. This is a C4P webinar. C4P is an NSF-funded activity to help network scientists. And the talk this afternoon is about paleocoordinates on geological data from the ocean floor. So we have constructed a very large database of samples and observations from the seafloor. It's called dbSEABED, database seabed. And so this is a pretty interesting structure, and it's creeping up on the task of computing a worldwide geology. So many of you would have heard of one geology. That's fine for the continents, but the task of doing that for the oceans is much, much greater. So we're going to need large databases for that. Paleocoordinates are the true coordinates in latitude and longitude that applied to a sample when the sample was formed or when it was changed. So the paleocoordinates are very important because they locate a sample in the correct climate and oceanographic zonation. Ocean drilling program samples are fine and they can be related to each other geographically, but for a true picture you really need to transfer them back into paleocoordinates. So that's what this talk is about. Okay, so I'll just say a little bit first about dbSEABED. In my view, and I think this is correct, it's the largest, most active richest database talking about the materials of the seafloor. It's the whole seafloor, from the coast right down to the abyss. It deals with the materials. It doesn't deal with the water depth so much. It deals with the materials of the seafloor, their features, their ages, their physical properties like porosity, their compositions like how much diatom there is in them or how much carbonate. So the size of the database is that it's nearly 5 million sites worldwide, and all of those sites have some sort of description of the character of the seafloor. So this really is a huge resource, and of course it can feed into GIS and all those software systems. Now dbSEABED actually isn't quite a database. It's an information processing system. And so we've got a very strong focus in this unit on computational methods. And the reason why that's necessary is because seafloor data is so variable. I mean, people describe samples. They look out the portholes of submersibles and describe what they're seeing. They take a sample to the laboratory and do exquisite analyses on everything in the sample. So we have to handle word-based data as well as numeric data. And of course, there are many, many shades of all of those. So what the business that we're in is heterogeneous data integration. And a large part of that is dealing with word-based data. Actually, for all those sites in the ocean, about 85% of them are described in terms of word-based data. And that is also true, by the way, of the age data. So what's the distribution of the data across the oceans? Well, first of all, we have the very large programs, very long-lived programs, Ocean Drilling Program, Deep Sea Drilling Project, and those. And they account for around about 1,300 or more sites worldwide where we have terrific penetration of the seafloor, terrific collection of material and parameters, and terrific age dating. So this is really the king of the data sets in this business. But 1,300 sites worldwide is not enough really to get a full story. So dbSEABED is fairly strong in this because we also have dredgings, we have other drillings, we have many cores, we have underwater outcrop records, and many of those are dated, right? We know the geological age for them. So that brings the total tally of cores and samples that have age dating up to sites that have age dating up to about 7,000, just over 7,000. So this is starting to be a workable size for looking at ocean geology. It's a huge resource. And what's more important in some ways is that the resource is already fully integrated. So I'd like to thank some institutions that have worked with us on this to get the stratigraphic side of dbSEABED right, and that includes USGS and Lamont particularly. Okay, so way back in 2008, and I've got this fuzzy picture to provide evidence of this, way back in 2008, Lamont and Instar worked together to explore what would be needed to get a global stratigraphic geology of the oceans. And this was with Bill Ryan and myself and some of his students. And so here we have a diagram that looks like a molar tooth. And it looks like a molar tooth because the mid-ocean ridge is separating the two sides of the ocean. And you can see from this, the blue carbonate facies has a distribution on one side. The high terrigenous facies is visible on the African side. This is the transect of the South Atlantic. And and then there are various mineral and feature occurrences. And this diagram was made automatically in ArcView 3.0 straight off dbSEABED data. And so this first effort proved that it was feasible to take ocean stratigraphic data and make a global or ocean basin scale transect. All right, so this brings me to paleocoordinates, because that first effort was in present-day coordinates. And that was the wall that we ran up against, that it didn't seem to be possible really to transfer all the sedimentary observations into paleocoordinates. And I'll just take a little moment now to illustrate why this is necessary. So here we have an IODP core, actually an ODP core, I'm sorry, which was drilled in the East Tasman Plateau, east of Tasmania. And it was ODP leg 189, and it drilled all the way back to the late Cretaceous. So if you consider each of those little samples in the core, where they were when they were first formed, you realize that actually the whole core lies along a trajectory that stretches from East Antarctica around the Southern Ocean and then finally ends up in the East Tasman Plateau. So any core that has deep time actually represents a pathway or a trajectory in latitude, longitude, and age. So this is really the problem that I'm talking about this afternoon. So each of these cores that we have is sort of a snake or a worm that goes through spatial temporal coordinates. Now the big thing that's changed is the wonderful effort by the G-Plates team to compile all the plate tectonic motions and interactions into one software system. So I totally commend G-Plates. And so you can see these paths on the globe here are the trajectories of lots of ocean drilling cores. And you can see that they are really wandering around. The East Tasman Plateau core, for instance, wanders by 23 degrees of latitude. And that represents moving through quite a few oceanographic zones of the present day, let alone of the developing Southern Ocean. So yeah, so G-Plates is a vehicle where we can transfer the observations that are made in the present day drill core at its site into paleocoordinates. And the paleocoordinates change as you go down the core. G-Plates was what we used to do the paleocoordinate computations. So we were only able to do it for a small number of cores, and one of the reasons for that is because in many cores there's not a good age model, or there's some other defect in the available data that we haven't fixed yet. But this plot here shows the overall results going from red in the 100 million year time up the diagram to blue at the present day. And the two panels are the continent-ocean boundaries of those two times. So the lower panel is continent-ocean boundary at about 100 million years ago, according to G-Plates. And then the top panel is continent-ocean boundary today. And you can see that they're upside down, so you can see South America and Africa sort of pointing upwards on the screen. Pacific Ocean is over on the right, and then Australia is over on the left. And of course Asia is at the bottom of the panel on our screen. So some of these cores have really wandered around, right? And if you look at the one track that seems to be whizzing off by itself, that is what we find with some of them, that they really do have quite a dramatic pathway, and they've carried the observations and the sediment properties with them as the core has gone along its trajectory. Okay, so this diagram can be a little confusing to look at to begin with, but have a look at it, and I'm going to post some rotating versions so that you can really get a view of it. By the way, you can see the cores in the Pacific Ocean making their way westward on the left-hand side, right-hand side of the diagram. And then on the very left-hand side of the diagram, you can see those same cores colliding with the Western Pacific Island Arc Complex including Japan. So you can see the whole slew of them making their way up to collide with the subduction zones there. Now, so we've got that. So we've got the paleocoordinates and the ages, and we need to attach the parameters out of the cores. For instance, we might want to attach the carbonate values. A carbonate is actually a pretty good first parameter for us to make an assessment about the paleoceanography. So this diagram here colors the age occurrences by carbonate value. And you can get some idea of some sort of local coherence out of the diagram, but really what we need to do is to develop a better form of visualization so that we can get a more immediate view of what's going on. We also need more data. So carbonate is not the only thing that we could plot. Out of dbSEABED immediately we could plot the sediment colors. We could plot the sediment grain sizes. Immediately we can plot the smear slide and lithologic description, contents on things like planktic forums, diadems, radial area, various minerals, glauconite. We can plot the occurrences of bioturbation and so on. So by combining G-plates and dbSEABED in this way, I think that we can bring a really rich resource of sediment properties right up alongside the paleogeographies of the last 100 million years. So what was involved in creating this diagram? Well, first of all, there's the aggregation of all the data in dbSEABED, a long effort, a lot of computational methods, including fuzzy set theory, uncertainty analysis, interpolation on maps, various tools to bring the data in from multitudes of formats. A lot of colleagues have helped with the hard coalface work of entering data from texts, spreadsheets, and so on. So this effort is not to be underestimated. It's really a huge effort. But once that's done, then in a sense the fun begins with visualization and analysis. So part of that fun is to bring all of that aggregated data up right alongside G-plates to bring it into paleogeographies. So to do that, one of the first operations is we need to identify which present-day plate the samples belong to. So with the ODP drill holes, that needs to be done. So a drill hole might be on the Australian plate at the moment, or might be on the African plate. And so which plate it belongs to will determine its backwards graph of the past plate tectonic motions. G-plate handles that networking and that graph. So, all right, so after that we assign an age to each sample. This is also quite a difficult operation because we need to work with all the age models that have been published, and they are really scattered around the internet. So we have age models in Chronos System, in GeoMap app, we have some in the Ocean Drilling Program itself, we have many more in Pangaea. So those age models are really scattered, and I think that our community needs to work to index them at least, so that the ages can be brought up against the samples. So once that's done, we submit the whole matrix to G-plate, and we did that in a GPML format. But one of the things I'm really pleased to note is that G-plates, I think, now have a new way of doing that, which is much more automated and much more efficient process for the user. So that's good. And lastly then, so we extract the paleo coordinates from the G-plate reconstructions, and then what we do is hold them either in a matrix or in a database fit for visualization, time slicing, and just doing all sorts of data analysis operations. So that's can now be done on the matrix that you're seeing in front of you. So we're making this matrix available to people to analyze in whatever way they want to. We've also planned to increase the amount of data in this matrix, and we have a number of ideas on how to do that very quickly. It's most important, really, that this is done for the continental margins. They're not sampled very well by the IODP, but there are many avenues for bringing in dredge and core samples from those continental
Hi, Chris, 3 minutes.
Okay, good, we're on time. All right, so just to begin the wrapping up, what has to be resolved? Well, first of all, many cores exist with age dating, but actually, when you look at the core in detail, the age dates can be quite sparse in the core. So this means that the measurements of grain size and fossils and carbonate and so on, organic carbon, they need to be merged in a smart way with the age model data. And I'm looking to new pieces of software, and maybe the next talk is interesting that way, new pieces of software which will allow us to do that in a smarter way. We need a wider set of parameters for analysis. Obviously, carbonate is not going to satisfy everybody, but we already have quite a lot of parameters in dbSEABED. We need to boost the amount of age-dated data. So this is what I referred to before. We especially need to do that for continental margins. And we need better tools in the community for visualizing, time slicing, and databasing. Okay, so thank you for listening. And what I'd like to do to close is to say thank you to the many, many people who've helped dbSEABED and my science in particular. Thank you very much. In return, dbSEABED works very closely with universities, and we give data sets out gratis to research projects. We have to be a little bit careful with dbSEABED because sometimes it can be misused by fishing fleets and so on. So that's the reason why dbSEABED is not totally public. But come to us and ask us for data. Finally, here are some references that might help if you want to explore this further. So all the references in the PowerPoint today you'll find in that poster from ESIP. Otherwise, I'm looking forward to potentially working with people, and we'll continue to make this facility stronger. Thank you very much.
Thanks a lot, Chris. And you actually answered one of the first questions here, which was, do you need to become a collaborating member to use dbSEABED? So I guess just to repeat that, if someone would like to collaborate, they should contact you. Is that correct?
Yes, that's right. So, I mean, dbSEABED is actually a wide collaborative network. You can see how wide on its website. It's used in Germany, Australia, New Zealand, the US, and a number of other places. The best way is to work with us. And what I will point out is that we do make data available free for research theses, right? PhD, MSc, honors, and we enjoy doing it, really. But the best way is to collaborate with us.
Okay, thanks. The next question is, what are the bottlenecks for getting more data into the system?
Yeah, time and motion. So, we know where the data is, but it actually takes quite a lot of time to bring data in a reliable way. So I'm interested in machine learning ways of doing it quicker, but until they're developed, we really have to do it sort of manually, sort of case by case. And so some months we will bring in 50,000 new sites for data in dbSEABED. There are some wonderful data sets out there. But in every case we have to bring it in and then we have to check it. And usually we leave data sets for a year until they graduate to the main database. So this is the main bottleneck, is the data entry. So one of our slogans is that we only want to do it once. Do it once, bring it into dbSEABED, and then we have many, many uses from there. Okay?
All right, thank you. There's another question which you seem to have answered with one of your last slides. I'm not sure if maybe you can put it up again, but this question is, where do we go to learn more about the technical issues addressed in dbSEABED? And I think those poster links that you put up may answer that.
Yeah, I think so. So the eSIP poster talks about today's topic, right? And there's a lot more information in the poster. So I really recommend having a look at that. For the issues in dbSEABED, just go to the website. The technical issues are largely described in the papers that are in the bibliography. But the website's interesting, and then of course if you have any questions, just give me a call. Just email, or there are other partners too, University of Texas, Lamont and so on, and they handle special issues in the system. Okay.
The next question is, what are the search capabilities in dbSEABED? If you want to search, we're assuming like by location or something, but what are some other things you can search by to find the data?
Yeah, so as it's operated by the partners, I mean, these partners have a full copy of. So we didn't want to prescribe the way people use it. It can be used in MATLAB. So you don't really need to query it so much, you just need to slice it. And the data model we have on the final product is a hypercube. So if you want to, you can slice it by age and then organic carbon, right? It's like a NetCDF concept of data. On the other hand, I mean, some of the people I work with in Germany, they put it into a full-blown relational database, and they have fun with it that way, right? So the data is GIS ready, it's ready for relational databases, and it can also be dealt with as a hypercube. Yeah.
Okay. We have one last question here, and a reminder, please just chat in the window. And we're having fun with this new interface. Everything is new, so it's not what we're used to. But if you just chat to the Research Coordination Network's participant, we will read out your question. So this last question is, I saw on the web page that there's a partnership with the Deep Carbon Observatory. Can you talk a little bit more about what does that involve?
Yeah, so that's a partnership. It's three-way with DCO and Lamont and Instar. And the Deep Carbon Observatory, we're interested to get a better handle on how much carbon has gone down the subduction zones, down with the plates. No, and this is a question which had a very nice answer to it some years ago. I'll have to remember the author's name. But with all the new data, we thought we'd take a new look at it. And that collaboration was one of the spurs for us to get into the paleocoordinates. So once we have the paleocoordinates on the organic carbon values and carbonate values, then we can actually attach times that carbon went down the sink, right? So we get a time-sliced picture of how much carbon has gone down which subduction zone. Now, the data are a little bit thin at the moment, right? But the nice thing is that we have the technique, thanks to G-plates and dbSEABED, to work out the time and place that various carbon-rich formations went down the subduction zones. So that's the answer I give to that. Yeah.
Great. Thank you very much for your answers. Those are all the questions we have at this time. So I'm going to go and give the screen share to Jim and unmute him.